All right, good morning, everybody. Before we get started on today's material in Chapter 2, let's briefly review some of the things that we covered in Chapter 1. What were some of the topics we covered? We covered hybridization. What does it mean to have something that's hybridized? Orbitals combine. Well, orbitals can actually combine in a way that forms bonds, but that doesn't necessarily mean hybridization in and of itself. What does it mean? In other words, I can have two orbitals combine to form a bond, right? But bonding isn't necessarily hybridization. So what does hybridization really mean? Occupying the same space. Okay, that is certainly true, right? So what we're doing is we're taking, to make hybrid orbitals, what kind of orbitals are we working with? Okay, we're working with S and Ps. We're really working with atomic orbitals, right? Things that exist in the atom as it is on the periodic table. And then we are combining them in a way, right, in which we generate new orbital geometries, right? So a p orbital looks like a dumbbell, but an sp3 orbital, not exactly a dumbbell. It looks more like a dumbbell than a sphere, right? But it is nonetheless a different geometry, a different arrangement of the orbitals that we're looking at. So if we start off with 4 orbitals and we hybridize them, how many new hybrids must we get? 4. They are conserved. We start with however many orbitals we're going to hybridize, we have to end up with that many orbitals. We can't create nor destroy an orbital. What other things did we talk about in Chapter 1? We talked about shapes, molecular structures. Okay, very good. Harkening back to Vesper theory a little bit from your general chemistry. What else did we talk about? Talked about resonance structures, very important. So resonance structures depend on our ability to draw a proper Lewis structure. And so we talked a little bit about how we can represent organic structures, and we talked about several different types, right? We talked about the linear structures where we just draw the atoms and the how they're connected together, right? And then we talked about condensed structures, and then we talked about, what was the other one? Skeletal or bond line, depending on which book you're reading, right? And so, which is most common for us as organic chemists? Skeletal. It's a lot quicker to draw a skeletal structure than it is to draw any of the others. Now, there's some assumptions you have to make in the skeletal structure. What are they? Hydrogens are not explicitly shown that are attached to what? Carbons. However, if they're on heteroatoms, we must draw them. What else is an assumption? Lone. Okay, so each vertex, right, is a carbon atom in the zigzags that we draw. What else? I think I heard lone pairs, right? So if I have an oxygen, for example, like I have up there, notice I did not draw the lone pairs on the oxygen. But I know they have to be there. How many lone pairs are actually there? 2 or 4 electrons, right, as 2 pairs. That's exactly right. All right. So today we're going to continue on and build on that, and we're going to start talking about hydrocarbons, the types of hydrocarbons that we can have. Hydrocarbons are the foundation of organic chemistry, okay? We're going to start talking a little bit about polarity. You've talked a little bit about that in general chemistry. All polar molecules must have what? Polar bonds. Partial can come into it. You're not incorrect there, okay? But do all polar bonds lead to polar molecules? No. So it's not just electronegativity differences that we have to pay attention to, but also shape in 3 dimensions, right? And so again, like I said, I think on the first day of class, structure is function, right? In organic chemistry and actually in biochemistry. Biochemistry is an offshoot of organic chemistry. Most of the biomolecules are organic molecules that you'll be dealing with. So 3-dimensional shapes and things lead to differences in polarity, lead to differences in reactivity, lead to differences in function. Very, very important. So we'll talk a little bit about polar and nonpolar molecules today, and then we're going to start talking about functional groups. So we're going to figure out what a functional group is and how we identify them. If you hear that term functional group, what comes to mind? What does function mean? Okay, has a purpose, has a particular reactivity. And it turns out that organic molecules can be quite large, can be quite complex. But it turns out if you have a functional group in a small molecule and you have a functional group in a large molecule, they behave essentially the same, okay, at the first level of understanding. And so if you understand something about functional groups, regardless of how big the molecule is, you can get an idea of the chemical reactivity of a molecule. Where is it going to react with a chemical? Where is it most likely to break apart? Where is it most likely to have a function that leads to a biological process? All of that comes down to our understanding of functional groups, to be a little bit oversimplistic, but yeah, I think it's a good start, okay? So let's start talking about hydrocarbons. You hear the word hydrocarbon, what do you think? Hydrogen and carbon. These are molecules that only contain hydrogen and carbon, okay? And so some examples that you're all familiar with are methane, CH4, natural gas, okay? It is a hydrocarbon. All it contains is carbon and hydrogen. Also, if you look at ethane, C2H6, it is a hydrocarbon, which is quite commonly found in natural gas as well, but albeit in lower percentages than methane, okay? These are called saturated hydrocarbons, meaning we can add no more hydrogen to that number of carbons that are in the molecule. If you think about methane, CH4, and you draw it out the long way, why can I not add any more hydrogen to that carbon? It's got a full valence. It has satisfied the octet rule. If I put a fifth bond to carbon, it doesn't have the orbitals to accept those electrons. It has no place to put them, right? So I've got as many hydrogens as that carbon can possibly handle. It is saturated. Where have you all heard the term saturated or unsaturated? Fats. And that's exactly, it's the chemistry. Saturated fatty acids are what? What kinds of things do you think of as saturated fats? Huh? Butter. And everything's better with butter, isn't it? Right? Butter. Lard. They're saturated fats. Okay? Are they healthy for us? Not particularly. What do you think about when you hear unsaturated fats? It doesn't have as many hydrogens, that's true, but that's getting into the chemical part of it. You're absolutely right. Okay? But what do you think about if you know, just in general, if somebody said unsaturated fat on a commercial, what would you think? Healthier. Healthier, okay? Olive oil. A lot of oils have unsaturations, and that's what makes them liquid, whereas saturated fats are typically solids, right? So, yeah, a lot of stuff like that. And so we're really talking about hydrocarbon chemistry here when you hear that kind of stuff on the news or on some television commercial. Now, ethene and ethine are unsaturated hydrocarbons because if you look at it, C2H4 I don't have all my valences yet, right? How do I get a full octet for everything? I have to have a double bond between the two carbons. That's an unsaturation, okay? So anytime you are minus 2 hydrogens in a molecule, it's said to have 1 unit of unsaturation. Why? Because I can add 2 more hydrogens to this, right? And I could get ethane. So ethane and ethene are only different from one another by 2 hydrogens. This is saturated. This is unsaturated, okay? Unsaturated hydrocarbons can be things that are called alkenes or alkynes. Alkenes have carbon-carbon double bonds. Alkynes have carbon-carbon triple bonds, okay? So we can talk an awful lot about those types of hydrocarbons, okay? There's another set of molecules called aromatic hydrocarbons, and these are a class of hydrocarbons that have special electronic and chemical properties. They don't react like you would predict based on their unsaturation. We're going to leave that section of chemical talk, though, to come from a future chapter when we start talking about aromatic rings like benzene and other things like that. Okay? So let's talk about the simplest hydrocarbon, and that's methane. Okay? It is the major component of natural gas. Most people think natural gas is completely methane. That is not true at all. It's only somewhere between 60 and 80%. So if you go out and drill a natural gas well, up to about 80% of that gas is going to be methane. The other parts are going to be ethane, butane, other types of hydrocarbons that are found in these deposits. It turns out that we have large industrial interest in methane. Okay, we spend lots and lots of money to recover methane, natural gas every year because it's a very valuable commodity. We use it a lot as fuel. Okay, this is what many of you heat your homes with. This is what many of you heat or cook your food with. If you have a gas stove, you're really cooking with natural gas, right, which is mostly, again, methane. We generate a lot of electricity nowadays using methane. Still in the United States, we use a lot of coal to generate electricity, but methane is actually cleaner. It's the cleanest of the fossil fuels. Can anybody tell me what we mean by clean? Pollution-wise, that's exactly what we're talking about. When I burn a hydrocarbon, what do I get? I get CO2 and water and energy. That's right. I get CO2, water, and energy. When I burn when I burn coal, I don't just get CO2, water, and energy. I get those, but I also get sulfur dioxide. I get mercury emissions. I get soots that are carcinogenic if you happen to inhale them. You get lots of stuff in addition to carbon dioxide, water, and energy. That does not mean that the burning of natural gas is completely environmentally friendly. It's just of the fossil fuels, it is the most environmentally friendly that we have. Okay, so it works better for us than coal, or works better than coal and/or petroleum or oil-based products. Okay, methane is produced by bacteria called methanogens. And if you put these methanogens under oxygen-free conditions, they decompose organic matter into methane. Okay? These microorganisms are found just about everywhere that you can think of. They're found in trenches, they're found in mud, they're found in sewage, and they're found in the stomachs of cows. Okay? And they generate a lot of methane. Cow flatulence contributes more to global warming through methane emissions than just about anything else that we can control. Just a fact. I still like my cows, but it's a fact, okay? If you've ever gone out and in the swamp and you've seen things bubbling, it's methanogens generating methane gas. There are places that you can go where you see bubbles coming up from ponds and swamp areas and stuff, and you can light it. It's actually a flammable gas. You can Google that and find places all over the world where natural gas is just bubbling up out of the ground, and people try to have fun with it and set it on fire and watch it on top of the water for a while, and it's kind of cool to watch. Okay? But just about anywhere you can find these methanogens. Very large deposits of methane are found deep in the ocean, called methane hydrates. Again, you can Google and see some video of this. These are beautiful crystal-like structures that exist deep in the ocean. Okay, where this methane is apparently bubbled up, and for whatever reason I'm not completely clear on, it freezes with the water and forms these hydrates. It is believed that if we could economically harvest the methane hydrates in the depths of the ocean, now we're talking miles and miles and miles and miles and miles down for this to happen. It's not like right at the beachfront. Okay, we would actually not have much of a fossil fuel problem in terms of energy production. We'd be able to run for very long times without having to punch another hole in the earth for quite some time. Okay? Methane, as you know, has all carbon-hydrogen single bonds. It is a tetrahedral arrangement, and those bond angles are 109.5 degrees, and those hydrogens are all equivalent, meaning if I hold it this way or I hold it this way, I can't tell any difference. All the carbon-hydrogen bonds are equivalent in methane. And so would you consider this to be a polar or a nonpolar molecule? It is nonpolar. And it is nonpolar for two reasons. Number one, carbon and hydrogen have very little difference in negativity, electronegativity. There is some, but it's very small. And two, the tetrahedral geometry around it, no matter how I turn it, I can't see anything different. And so the symmetry also dictates that it not be polar as well. Okay? So let's start talking about alkanes. This is the first group of hydrocarbons that we need to talk about. These are also known as aliphatic hydrocarbons. You will have people, when you take biochemistry or biology classes, refer to them as aliphatics. Okay? It's just an alkane. All aliphatic hydrocarbons, the only thing that they contain by definition is carbon-carbon and carbon-hydrogen sigma bonds. There are no pi bonds in an alkane. Okay? And so we have all sigma bonds. Okay? Now, acyclic alkanes have the molecular formula of CnH2n plus 2, where n is some integer. What do I mean by acyclic? Not cyclic. And what does that mean? Linear. Okay. So let's say we have that. How many carbon atoms do I have in that structure? I have 4. 1, 2, 3, 4. So C4. So without actually drawing in the hydrogens, predict using the formula of what my H number should be. 10. Right? Because it's CnH to the 2n plus 2. And in fact, that's correct because I can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? It is considered what kind of hydrocarbon? It is acyclic, that's true, but it is also saturated. Okay? All acyclic alkanes, by definition, have to be saturated. Okay? And so something like this, C7H16, we say that that is a straight chain alkane. Now wait a second, the chain that I drew was zigzag, so why do we call it a straight chain alkane? Nothing's branched, and if you actually wrote it out, you would write it out in a straight chain. Okay? But we know that the real shape of it is a zigzag shape, right? Because we're putting together tetrahedra. Cycloalkanes, okay, have at least a single ring. There we have something that looks like a stop sign. How many carbons are there in that structure? 8. Hydrogens? 16. It fits the formula CnH2n. Is it saturated or unsaturated? How many could I have for C8 if it was saturated, if I followed this equation? I could have 18, right? So is it saturated or unsaturated? It is unsaturated. And why is it unsaturated? I don't have a pi bond. Why is it unsaturated? I could have more hydrogens, but why can I have more hydrogens? Why don't I have as many hydrogens as I need? I see people doing it with their finger. Tell me why. If I took the saturated alkane, C8H18, right? How many hydrogens do I have to remove to make the ring? 2. I have to remove the 2 from the ends, right? If I remove the hydrogen on this end and a hydrogen on that end, that allows me to connect those 2 carbon atoms together to make the ring. So unsaturations can actually come from pi bonds or rings or a combination of the 2. Okay? So even though this is a alkane and not an alkene or an alkyne, it is nonetheless an unsaturated hydrocarbon because for 8 carbons, I should be able to have 2 more hydrogens than are shown in that molecular formula. Okay? So let's summarize a little bit. You're going to be responsible, at least on the first exam, knowing everything through 10 carbons. You need to know the names of everything through 10 carbons. Okay? So 1 carbon is methane, 2 carbons is ethane, 3 propane, 4 butane, 5 pentane, 6 hexane, 7 heptane, 8 octane, 9 nonane, and 10 decane. The molecular formulas are quite simple. They all follow the CNH2 or 2N plus 2 rule, right? All the way through. Here's the names. The number of constitutional isomers. What is a constitutional isomer?
A molecule with the same atoms is arranged in different order.
That's right. It has a different constitution. It's connected differently, right? Methane, there's only one way to put those 4 hydrogens and that carbon together, and that's to put the carbon in the middle and the 4 hydrogens around. You have no constitutional isomers for methane. Ethane, there is only one way to take those 2 carbons and those 6 hydrogens and put them together. For propane, there is only one way to take those 3 carbons and those 8 hydrogens and put them together properly, and that's to get propane, okay? When you get to butane, we start to have constitutional isomers. So C4H10, there's C4H10. How else could I put that together to get another constitutional isomer? Branch off from the second carbon? Is that still C4H10? You bet. Is that the same as that? Absolutely not. These are the only 2 ways that you can put 4 carbons and 10 hydrogens together in an alkane. Okay? Now notice if you go to pentane, you have 3. You go to hexane, you have 5. You go to heptane, there's 9 possible. Things start to get pretty big pretty quick, right? For decane, if I have 10 carbons and 22 hydrogens and I gave you those in your model kit, you would come up with 75 different ways to connect those together. 75 different ways to put those together. Now, if I double the number of carbons, I go from 75 not to 150, but to 366,319. I think it goes without saying that you're not going to be responsible for all 366,319 different constitutional isomers of icosane, okay? Nor are you going to be responsible for all 75. What I want you to understand here is that with a small number of carbons and hydrogen atoms, we can generate a large number of molecules. That is the importance of organic chemistry. Carbon can form so many different types of structures. These are different structures. They have different physical properties. They have different chemical properties. They are different. 20 carbons is a small molecule, and there are 366,000 different ways to make molecules from those. That's kind of cool, right? There's no other element on the periodic table that can do this. That's why I love carbon, okay? That's why you should love carbon. It's because it gives us everything that we use, right? Think about everything that you use, and I'll guarantee you most of it is organic. The materials that you're wearing in your clothes, organic. The materials in your car that make it more fuel efficient, organic. Plastics, medicines, the whole 9 yards. It's organic chemistry, okay? And so what would be a fair thing to expect you to do on an exam? A fair thing on an exam would be, I don't know, say hexane and above. I might ask you, which of the following is not a valid constitutional isomer for hexane, or something along those lines. You would need to be able to identify which one is not, okay? Or I might give you 4 of the 5 and ask you to draw the 5th, something like that, okay? I know you only have 50 minutes to take the exam. I'm not going to ask you to do everything, okay? It's just not possible. But you need to be able to do this. The easiest way to do constitutional isomers, use your model kit, okay? And we'll have more practice with that as time goes on. Not all carbon in a molecule is identical, even in an alkane. Even though all the carbons in an alkane are what hybridization? They're all sp3, but not all sp3 carbons are identical, okay? And that may sound a little strange, but there are things called primary carbons, secondary carbons, tertiary carbons, and quaternary carbons, and they have different chemical reactivities that we'll learn about later on in another chapter. A primary carbon is a carbon atom that is bound to one and only one other carbon atom. That's a primary carbon. That CH3 is bound to one carbon. That is a carbon-carbon bond. A secondary carbon is a carbon atom that is bound to two other carbons. This carbon is bound to this carbon, and it is bound to that carbon. It is a secondary carbon atom. A tertiary carbon atom is a carbon atom that is bound to three other carbons. This carbon is bound to this carbon atom, and this carbon atom. It's a tertiary carbon. And the quaternary carbon is a carbon that is bound to four other carbons. For example, here, it is bound to four other carbons. Some people, when they're looking at alkanes, will identify these not by the number of carbon bonds, which is how I do it, but by how many hydrogens are on the carbon. Notice a primary carbon has to have three other valences, and those are by hydrogen. A secondary carbon will be a CH2. A tertiary carbon will be a CH. And a quaternary carbon will have no hydrogens on it. So you can identify them multiple ways. But personally, it just makes more sense to me to look at the number of carbon bonds. But whatever works for you, it doesn't matter. Okay? Let's do a quick concept test. Give you about a minute here. How many primary, secondary, tertiary, and quaternary carbon atoms exist in the following molecule? How many primaries do I have? I have 6. 1, 2, 3, 4, 5, 6. How many secondaries? 2. How many tertiaries? I've got 2. I've got one here. I've got one here. And how many quaternaries do I have? 1. Notice I have different types of carbons within a single molecule. However, all of those carbons are sp3 hybridized. It is a true alkane. It is a pure hydrocarbon. Let's talk a little bit about alkenes. This is where we start to get into things that are kind of useful for us. Alkanes we largely put in our car and just burn them or heat our homes with them. But alkenes, we actually start to get stuff. Okay? And so the simplest of these are ethene and propene. These are important industrial chemicals used to prepare polymers. How many of you are in polymer science? So a few of you. You're going to be talking an awful lot about alkenes in your courses and in your laboratory work. Okay? So for example, you can take ethene, which is also known as ethylene, and we can make what's called polyethylene, which is a plastic. And when these slides were put together, these slides are getting a bit long in the tooth now, so these numbers are probably not quite accurate. 30 billion pounds per year in the United States of polyethylene is made to make polyethylene tapes, polyethylene sheet, polyethylene plastic coatings, polyethylene bottles, milk jugs, the whole 9 yards. 30 billion pounds per year. That's not a small number, right? 30 billion is a lot. Propene is actually polymerized to make what's known as polypropene or polypropylene. 15 billion pounds per year in the United States. Polypropylene is used to make other materials. AstroTurf, for example. Okay? Very, very important. Simple, unsaturated molecules can actually be utilized to make these very important industrial materials. Alkynes. We're talking about carbon-carbon triple bonds here. They are still unsaturated. The simplest is ethine, C2H2, and it's an important industrial gas. Okay, for if you've ever done any type of welding with a torch or seen somebody doing that, they're using acetylene or ethine. Acetylene is the common name for it. Okay, so if you've ever heard of oxyacetylene torches or torch welding, that's what we're talking about. It burns really, really hot. But it's also used to make other types of organic molecules. We can use the carbon-carbon triple bond as a unit, as a functional group to make other types of organics. So for example, we can use carbon-carbon triple bonds in molecules like capelin, which is an antifungal agent. If I take these triple bonds away and I replace it by saturated carbon-carbon bond, or carbon-hydrogen bonds, excuse me, it's not an antifungal anymore. Dactyline has both a carbon-carbon double bond, but it also has a carbon-carbon triple bond and some other stuff out here. It too is an antifungal. And this is an estradiol, ethenyl estradiol. Okay? It is otherwise known as the pill. Okay? It is an oral contraceptive. It mimics estrogen. Okay? It has a carbon-carbon triple bond right here. If I take that carbon-carbon triple bond and I add hydrogen to it and make it saturated, it no longer works. You need the carbon-carbon triple bond. That would be quite the disappointment, right? You need the functional groups to make this work appropriately. Now, there's other functional groups in those molecules. There are also rings, but we're focusing just on the carbon-carbon triple bond part. Benzene, we'll talk briefly about it. It is an aromatic molecule, okay? Benzene is the simplest, or the most common, I should say. It's actually not the simplest aromatic hydrocarbon, but it's C6H6. It looks like this. What else? What does that look like? If you didn't know it was benzene, does it look like an alkyne, an alkane, or an alkene? Looks like an alkene. Looks like a bunch of carbon-carbon double bonds. It does not react or behave like carbon-carbon double bonds. And that's why it's separated out as what's called an aromatic compound. And we'll talk more about that in another chapter. But it is a hydrocarbon. It contains nothing but hydrogen and carbon. Just out of curiosity, how many units of unsaturation do you see there? What is a unit of unsaturation again? A deficiency of 2 hydrogens. Absolutely correct. So how many units of unsaturation do you see there for 6 carbons? It actually has 4 units of unsaturation. 3 are very obvious. The double bonds, right? I can add 2 hydrogens there, 2 hydrogens there, and 2 hydrogens there to have 3 units of unsaturation. Where's the 4th one come from? The fact that it's a ring. Remember, a ring is a unit of unsaturation, and pi bonds are also units of unsaturation, right? So that's where you get the 4 units of unsaturation for benzene. The cool thing about hydrocarbons and organic molecules in general is you don't have to have one type of hydrocarbon to make a molecule. Okay? So if we look at this particular molecule, this is called alpha-prostol. This is used in veterinary medicine for estrus control. Okay? Notice it has parts that are saturated, unsaturated by rings, carbon-carbon triple bonds, carbon-carbon double bonds, some other functional groups we'll learn something about. But you put them in the right place, give them the right orientation, and you now have a molecule that is used in therapeutic, has a therapeutic activity in the veterinarian realm. Does anybody know what estrus control is? If your dog goes into heat, they've gone into estrus. Okay, so this is used to control when animals, specifically mammals, go into heat for mating purposes. Okay, so you can control that. It's kind of important to farmers and people that raise livestock and other things to be able to control that cycle. Okay, and so they need compounds to do that. Let's talk a little bit about bond dipoles. What do I need to have a dipole? I need to have a polar bond of some type, right? I need to have poles, right? Dipoles. I need to have 2 opposite ends, if you will. Think about things in your everyday life that have opposite ends. Like your little battery, right? It has a positive end and a negative end. It has a dipole. The little magnets that you put on your refrigerator have dipoles, right? They have a north pole and a south pole. right? They have poles. And so what we're talking about here is the same thing but on a molecular level or on an atomic level, okay? So we're talking about differences in electronegativity that lead to some permanent separation of charge. So if I have atom A and atom B is more electronegative, it's going to pull those electrons in that bond to itself, and we are going to get a dipole, okay? And the A atom would be the positive end of that dipole, and B would be the negative end of that dipole, right? So here's some examples. Hydrogen fluoride, HF. It has a dipole. Hydrogen is less electronegative than fluorine, right? So we have a dipole. Water also has a dipole. Hydrogen being less electronegative, than oxygen. And so we have a dipole in that direction, okay? I think you all will agree that carbon tetrachloride, which is shown there, has polar bonds. Carbon is less electronegative than chlorine. There is a dipole. However, carbon tetrachloride is not a polar molecule because of its shape. No matter how you turn carbon tetrachloride, you always see the negative end of the dipole. And therefore, the molecule itself just looks negative on the outside. It has no differences. Okay? What other molecules can you think of that fall into this category that are common to you all? Carbon dioxide. Polar bonds, nonpolar molecule. Water is polar only because of its bond angle. If water existed like this, would it be polar or nonpolar? It would be nonpolar. Water would go from being able to dissolve salts to not being able to dissolve salts. Okay? You depend on the dipole interactions of salts for their solubility in water. Okay? Water obviously is a very important molecule. Life depends on it. It depends on it being this shape. If water turned out to be that shape, water would probably be a gas at room temperature. Okay? Water would not have the polarity needed to sustain life, and we wouldn't be here talking about it today. Okay? So we depend on this bond angle and Vesper theory an awful lot. Okay? So let's do another quick little concept test. Predict for me the shapes of all four of those molecules. What do we think for 4-formaldehyde? What's its shape going to be? It's going to be trigonal planar. I have a central atom with 3 things around it. That's your basic Vesper theory from general chemistry, right? What's the hybridization of that carbon atom? It's sp2. sp2 hybridized carbons are going to be trigonal planar about that carbon, right? Which way is the dipole going to go? Towards the oxygen. That's exactly right. It is a polar molecule. How about chloroethane? It's going to be linear, right? What's the hybridization of that carbon? sp. You're going to have linear geometries around sp hybridized carbons. Does it have a dipole? It does. In which direction? Towards the chlorine. Dichloromethane, what's the shape? It is tetrahedral. Does it have a dipole? It surely does. And in what direction? Towards the chlorines. Dimethyl ether, what's the shape? It's going to be tetrahedral, even around the oxygen atom. You probably call it bent. That would have been okay. But remember, we also have to take into account where the electron pairs are, right? They're also part of the structure. Is there a dipole? Yeah, towards the oxygen, right? So in that direction. Functional groups. We're going to talk about an awful lot of functional groups. We're not going to talk about all of them that you'll ever possibly need to know. You need to make flashcards or whatever works for you to memorize your functional groups. Functional groups, as far as I'm concerned, are like your ABCs. When you went into English class, you knew your ABCs. You knew how to put letters together to make words. And they focused on the words. I need you to come to class knowing your ABCs of organic chemistry. And your ABCs of organic chemistry are the functional groups. I have found over time that people who make flashcards of their functional groups and memorize them do a heck of a lot better in this course. Okay? If you can identify a functional group by sight, you're in good shape. Okay, so I would, on one side of your flashcard, draw a structure of the functional group, and on the back, draw the name, and work it both ways. Works really, really great. You're sitting down watching television, you got your flashcards with you, a commercial comes up that's boring you, run through your flashcards. You're waiting for your friend to get out of their class before you walk over and have lunch, go through your flashcards. Pull them out and go through your flashcards. This you have to drill on. A functional group is an atom or a group of atoms that have a characteristic chemical or physical property. It is the reactive part of a molecule. Most organic compounds have carbon-carbon and carbon-hydrogen sigma bonds. Okay? That's kind of a given. Okay? But you can usually identify functional groups by looking for things that are other than carbon-carbon and carbon-hydrogen single bonds. Look for heteroatoms. That is atoms that are not carbon and hydrogen. So if you see an oxygen, a nitrogen, a sulfur, a chlorine, guess what? That's going to be part of a functional group. Look for pi bonds. Pi bonds are very common as part of functional groups. Find pi bonds, find heteroatoms, you find functional groups. Okay? And so we can put all these together in different arrangements and have a unique organic molecule that will distinguish it from another organic molecule, and we'll learn how to figure that out. But the reactivity of the molecule, regardless of how big or how small it is going to be dictated by its functional groups. Okay? So it's very important that you understand functional groups. So let's look at a couple of examples. Ethane, this molecule only has carbon-carbon and carbon-hydrogen bonds. So we say it has no functional group. The functional group is the alkane, technically. But it just contains carbon-carbon and carbon-hydrogen bonds. The only thing I can really do with ethane is burn it. I can't readily do other things with it. Okay? Ethanol, however, has a functional group. The difference between ethane and ethanol is simply an oxygen atom. But notice I found the oxygen atom. This is the functional group, this OH, and it's called an alcohol. Oops, I'm sorry. Or a hydroxy group. Okay? Ethane, ethanol. A single atom, very different physical properties. What do you predict the physical state of ethane to be at room temperature? It's a gas, part of natural gas. What about ethanol? A liquid. If I inhale ethane, I will die. If I consume ethanol, I will become drunk. Very different chemical reactivities if I consume enough of it, right? Very different. And it's all because of one atom, okay, that makes a functional group. I've got some tables of functional groups for you. This is a great place to get started. Alkanes, no functional group. Alkenes, the double bond is the functional group. Alkynes, the triple bond is the functional group. Aromatic rings, like this, we call those phenyl groups. Okay? Those are the functional groups. They have different kinds of chemistry. If we have a carbon bound to a halogen, we call these alkyl halides, and the halogen is the functional group. If I have an OH, this is an alcohol, okay? And it's a hydroxy group as the functional group, okay? If I have a carbon bound to an oxygen that's bound to another carbon, like this is called an ether, okay? If I have a carbon bound to a nitrogen atom, like this is called an amine. I can have different types of amines. We'll talk about those more later. I can add a SH group to a carbon. This is known as a thiol. Notice it looks very similar to an alcohol. Sulfur and oxygen are in the same family, right? So I would expect similar chemistry. Yet, the chemistry that you all are probably familiar with these two is actually quite different. Methanol has no odor. Methane thiol stinks to no end. A drop of this molecule in this room would drive you out. It's molecules like this that they put in natural gas to give it its odor. Okay? Sulfides look like ethers, but with sulfur. Okay? So we have lots of different ways in which we can put atoms together to get functional groups. Okay? We also have what's known as the carbonyl group. The C double bond O belongs to a lot of different functional groups. Okay? Is that going to be polar or nonpolar? It's going to be polar, right? The C double bond O. It contains a carbon-oxygen sigma bond and a carbon-oxygen pi bond. And that carbonyl belongs to a large variety of functional groups. For example, aldehydes, ketones. The difference is this has a carbonyl hydrogen bond, this has only carbonyl carbon bonds. So on and so forth. We will finish up with this on Monday. I need you on your card on the front to write your name, print it, and on the other side, I want you to provide a topic from today that you found most difficult from today's lecture. I will look to see if there is a kind of theme of the class, and I will address that at the beginning of class on Monday. On your way out, leave your card up here, and also leave your inverted lecture. Make sure your name and your partner's name is on your inverted lecture. Have a great weekend. Sapling, Chapter 1 is coming due at the end, sometime next week. I think it's on the 31st. Chapter 2 is already up and available for you, so go ahead and get started. Have a great weekend.